Hello. Hello, everybody. Let me do the usual things. Where'd you go? There was something I specifically wanted to say. Now it's lost. Here's the usual stuff. Attendance, tutoring link, and the end of the quarter evaluation, which if you have not done already, please do it. It's not vital, but it is important to our office to get the feedback from the students. So if you haven't done the end of quarter eval yet, please do go ahead and do that. Let me go back and look here. I feel like I was looking for, I feel like there was something else I wanted to say, but maybe I'm just crazy. Like at the notes of our meeting the other day. No. Yeah, Nicole, I did get your email, and we can definitely go over some of the FAM stuff today. I forget, today is usually the MERCS day. Not that we can't talk about stuff from both classes, because I definitely think the FAM practice final stuff is good review for everybody. But today is the usual MERCS day, right? I think. Correct me if I'm wrong. But yes.
Yeah,
okay.
Yeah.
So there definitely is one MERCS question I want to address that someone else asked me, but then we can totally look at the problems from FAM's review. Also, as far as I can tell, MERCS hasn't posted any sort of final review yet. If he has, I have not been able to find it. If anyone knows of one, I would love to get it, but there might just not be one yet. I guess the thing I'm looking for is non-existent, or the thing I'm imagining exists is not really there. Sorry, yeah, just wanted to make sure. I guess there was something I thought was there, which isn't there. Okay. I did post a quiz that is very optional. You guys are all welcome to do it, but you're all welcome to ignore it as well. I'll post up some solutions to that probably tomorrow, so that if you want to at least look at how to do the problems I posted, that'll be there for you. I think that's about it. So for those of you in FAM's class, this next question is probably not going to be particularly useful, but we will look at it. And I feel like this question that he asked is kind of weird, but not once I thought about it, it wasn't too bad. So let me find it. There you are. Okay. So here's the question, which I'll write up in a second. A group of engineers is building a parabolic satellite dish whose shape will be formed by rotating the curve y equal to ax squared about the y-axis. If the dish is to have a 4-foot diameter and a maximum depth of 1 foot, find the value of A and the surface area of the dish. So it seems kind of weird, but it's actually not that bad. So here's what's going on. All right, we've got this parabola shape. And we're going to rotate this thing around, right? To get a paraboloid. Actually, it's not a paraboloid. It's not a volume. It's a paraboloidic shell. I don't know. It's a shell of whatever. So the idea is specifically, right, this parabola here is y equal to ax squared. And the way I'm reading it, and I just want to make sure maybe my interpretation is different, but I think the way this is supposed to be read or interpreted is that this is to have a 4-foot diameter. So that means we need, I'm going to think about it in terms of radius, right? I need this length to be 2 feet. And it's supposed to have a depth of 1 foot. So I need this to be 1 foot. So specifically, I need this point here to be the point on the parabola over 1 and up 2. And that's how we're going to figure out what the A value has to be. So if I need to go over 1 and up 2, it means when I plug in 1 for x, I should get 2 for y. So I need y to equal 2x squared is how I'm interpreting that. Does that seem reasonable to you guys? I mean, I think it seems reasonable. So hearing no dissent, Let's say that's what we got. So then we're trying to find the surface area of this thing you're rotating around. Now, let me point something out. If I'm finding surface area, it's the integral from a to b of 2 pi r ds. And this is a reminder, here's what we're really doing. This is going to be funky. So we're going around the y-axis is the way that he has phrased this. Double check that that's actually true. Yeah, okay. So as a reminder about how this kind of idea works, right? You're taking what I think of as a rubber band, right? So here's my, I can draw it like this. Right, there's my rubber band, and I'm trying to find the surface area of that rubber band. And the surface area of the rubber band is the circumference, which is 2 pi r, times the thickness, which isn't a dy or a dx, it's actually a ds because it's not a purely vertical or purely horizontal change. So that's where this is coming from. That's where that 2 pi r ds is coming from. So in this case, the radius is that distance there, which is definitely looking like an x. ds is always going to be, well, there's 3 different versions of ds. It's the square root of 1 plus f prime squared, or it's the square root of 1 plus, sorry, I should say, it's the derivative, it's the square root of 1 plus the derivative with respect to x squared, or plus the derivative with respect to y squared, or it's the square root of dx dt squared plus dy dt squared. In this particular example, since I've already got y as a function of x, I can just do it that way. Right, so I can do it as the integral of 2 pi x times the square root of 1 plus the derivative of y, sorry, so y prime is 4x here. That's going to be 4x quantity squared dx. Well, not the last thing, but the thing we have to think about is what are our limits of integration? And so here's where it could be easy to get tripped up. If you weren't being super careful, you might think the limits of integration were from -2 to 2. The problem is that would actually take this thing and rotate it all the way around half and then full, and you get double the surface area. We should actually just be integrating from 0 to 2, taking this right side of the parabola, rotating that fully 360 degrees around, or 2 pi radians. 2 pi radians. I look kind of crazy. My hair looks extra crazy today. I got clippers at the mail, by the way, so on Thursday you might see shorter hair if I'm brave enough to let my wife cut my hair. We'll see. I don't know. Anyway, so yeah, we're just going to go from 0 to 2. This is one way you can set this up. Let me actually show you the alternate way you can set it up. You can also do it in terms of y. And you can say, okay, well, the radius could be x, but you could also take this equation and solve for x in terms of y and get y over 2 and then square root of x. So you could also do this as the integral of 2 pi times your radius, which is still x, but now we're rewriting x in terms of y, square root of y over 2, times the square root of 1 plus, now instead of the derivative of dy dx quantity squared, it's going to be the derivative of this quantity squared. So I'm out of room here. So if x is equal to y over 2 to the 1/2, x prime is equal to 1/2 y over 2 to the -1/2 times the derivative of x 1/2, which is gross. But you could say right here I have that thing, which is 1/4 times y over 2 to the -1/2 squared dy. This integral would not be from 0 to 2, it would be from 0 to 1. Now, clearly one of these looks better than the other one, right? This second way, I wouldn't even consider if I'd already seen this first way. But it is worth noting that you can almost always do the surface area in 2 different ways, either with respect to x or with respect to y. you're going around the y-axis, the radius is x, or the radius is x as a function of y. And then you've always got this ds thing, which is the square root of 1 plus the derivative squared. So let's look at this version because it is nicer. It's actually really, really not terrible. So I've got here, really, really not terrible. It's so good. Oh, actually, by the way, fix my camera. It's a little bit better. We're getting the integral from 0 to 2 of 2 pi times x times the square root of 1 plus 4x quantity squared is 16x squared. And at this point, this should be not too bad, right? It's a straightforward u sub. We're going to let u equal 1 plus 16x squared. Du is going to be the derivative of 16x squared is 32x dx. I have an x dx, so du over 32 is x dx. So this part gets replaced with my du over 32. So this ends up being 2 pi times 1 over 32. That's my du over 32. And then I've got the integral of the square root of u. And I would probably change my limit of integration, although it's not particularly required. If x is 0, u is going to be 1 plus 0. And if x is 2, u is going to be 1 plus 16 times 2 squared. 16 times 4 is 64 plus 1 is 65. So 2 pi over 32 is pi over 16. Integrate u to the 1/2 and get u to the 3/2 times 2/3 from 1 to 65. Cancel a 2 here and a 2 here. I get pi over 24 times, plug in 65 and it doesn't simplify. You get 65 to the 3/2 minus plug in 1 to any power is 1. So it's not particularly pretty, but I think the hard part for when I was reading this question, the hard part for me was like, I don't understand what he means at first, that the depth is, 1 foot and the radius or the diameter is 4 feet. But all he really meant there is that you just have to figure out what parabola ends up at the point where you're over. Oh, I wrote that wrong. I got it right in the problem, but this shouldn't be the point. Ooh, I might have. Shucks. Or other words that start with sh. I think I made a small error. So the idea here is generally correct. But if I wanted this, I actually wanted this to be the point. I wanted that to be the point 2, 1, right? Because I wanted to have a diameter of 4, so I need to go over 2 and up 1. I got this kind of backwards. So, yeah, I think my a value is wrong the way I did it. If x is 2 and y is 1, a should be 1/4. So I mostly did this right, but not quite. I don't think we should redo it though. So I think this is a good example to have shown the Merckx people the problem. So what you guys are actually gonna have to do, instead of doing y equals 2x squared, we need to do y equals 1/4 x squared. So that if x is 2, y is 1. It's going to be very much the same problem, right? You're still going to find the derivative. Your y prime is going to be 1/4 times 2x, which is 1/2 x. And then that's what's going to go in here instead of 4x. But the process is still going to be pretty much the same. You're still going to do a u sub, right? You're still going to let u equal 1 plus whatever this is squared. And it's still going to work out essentially the same. I just got the coefficient incorrect. So hopefully for whoever asked me about that problem specifically, that was helpful. Sorry I didn't get it exactly right, but I think it's probably better than doing exactly the right problem. So that's the idea for that one. Are there questions about this before I start looking at some of the FAM problems? And Nicole, I don't remember exactly which problem you wanted to start with. If it was, I think it was problem 4. But I'm not.
Yeah.
Okay, cool.
You can jump around if you want. And I didn't know if you had a copy of it, so that's why I screenshotted it.
Can I jump up and get down?
Yeah.
So yes, you can. Hopefully you guys have the musical reference there. I know it's probably considered a classic, an oldie from crisscross. Anyway, definitely listed some crisscross when I was in 6th grade, for sure. Maybe 7th grade. Anyway, so I'm looking at the FAM midterm review, and we'll start with problem 4. And if anyone else has questions, feel free to jump in, either say something, or you can write something in the chat. So the problem here, and so these problems, I imagine his test is going to actually be like his practice, where there's a lot of multiple choice. So this is going to require being kind of extra careful with our work, because I'm imagining the answers he has posted, right? All the answers for problem 4 look very similar, right? You'll have a natural log of x and a natural log of x minus 2 and 1 over x minus 2. In fact, this problem is mostly, really looking at this problem, it's all about just finding the coefficients when you're doing the partial fraction decomposition. So let's look at what we've got. We've got the integral of x squared minus 5x plus 8 over x cubed minus 4x squared plus 4x. And all of the answers are 3 pieces. They all have a something times the natural log of absolute value of x, a something times the natural log of absolute value of x minus 2, and a 1 over x minus 2. So those answers definitely, even if we didn't think it was partial fractions before, the way the answer looks definitely says, oh, this was a partial fractions problem, right? We integrated 3 different pieces that we got by doing partial fractions and got those answers. So it also tells us how we have to factor this, right? I know I should have a factor of a 1 over x, a 1 over x minus 2, and a 1 over x minus 2 squared. So this fraction, x squared minus, I should say this rational function is not technically a fraction. This denominator should factor as x times x minus 2 squared. Also, let me give you guys the attendance stuff again. And yes, Sophia, I can look at number 9 for sure as well. Okay. Just taking this. Sorry, it's got a lot of it there. And we're setting it equal to, I'm going to write it as a over x plus b over x minus 2 plus c over x minus 2 squared. And remind me, how much time do you guys have for your final in FAMS class? Is it like 2 hours?
He said that we have an hour and like 30 minutes.
Okay. So what that says to me is you're going to have to be very efficient with your time, right? You're not going to have all the time in the world. So you're going to have to kind of you're going to have to work quick. And you're going to have to, so I'll make this point when I get a little further in this problem. Right. So it means, but what it means is like, you should be looking at the potential answers and be like, okay, how can I identify if my answer is one of those answers with doing kind of the least amount of work possible? So I'm going to start doing the thing, right? I'm going to multiply both sides by this denominator. I'm going to get x squared minus 5x plus 8 equal to a over x times this. The x's will cancel. A times x minus 2 squared. B over this times this. 1 of the x minus 2's cancel. And I get b times x minus 2. And then c over x minus 2 squared times this. The x minus 2 squared will cancel. I'll get c times x. And then I'm going to start using my convenient values of x. X equal to 0 is definitely one of them. And then plug in 0, I get 0 minus 0 plus 8 equal to a times 0 minus 2 squared. So that's a times 0 minus 2 is negative 2 squared is 4. So looking at this, I get a equal to 2. And right there, I'm actually going to stop for a second because I can answer the question right now. So knowing this a is equal to 2, I say, oh, that means whatever I get, I'm going to be integrating 2 over x plus some other things, right? But the integral of 2 over x is 2 times the natural log of the absolute value of x. And if we look at the answers, only one of the answers, in fact, let me show you guys. If I share my screen with you guys, right, if we look at this problem here, problem 4, only the second answer, or sorry, the third answer, C, has 2 times the natural log of the absolute value of x. None of the other ones have a 2 times the natural log of the absolute value of x. This is the only answer that can be right. Or sorry, C is the only answer that can be right. Now, we can still finish this problem, but just see, but what I'm trying to say here is that, right, if you're doing a problem like this and you get that and you are confident that that is the right coefficient of the natural log of the absolute value of x, that has to be the only answer, right? None of the other coefficients can change that this is that. So that can definitely save you some time on your exam. Let's still finish the problem though, just so we can see that the rest is correct. So I plug in x equal to 2, right, because that's my other convenient value. I get, let's see, 4 minus 10. 4 minus 10 is negative 6 plus 8 is 2. And plugging in 2, I get 0 here, I get 0 here, and I get 2 times c. So that gives me c equal to 1. So using that, I know I'd be integrating 1 over, so the integral of 1 over x minus 2 squared is the integral of x minus 2 to the negative second, which is x minus 2 to the negative 1 over negative 1, which is negative 1 over x minus 2. So looking back at the answer again, I see that C is still correct because negative 1 over x minus 2 does show up. And then we could use these to find, or we could use equating coefficients to find B. I look at the coefficient of x squared. I get 1 on the left, right? 1 is my coefficient of x squared. And on the right, I get a times x squared. I multiply this out with x squared. That's in lower terms. And I get b times x squared. Since a is 2, b has to be negative 1. And so I can see that when I integrate the whole thing, let's write that, yeah. So the integral of 2 over x plus negative 1 over x minus 2. So let's say minus 1 over x minus 2. Plus c, plus 1 over x minus 2 squared, or x minus 2 to the negative second. We're going to get 2 natural log of the absolute value of x minus natural log of the absolute value of x minus 2. And we said the integral of this was minus 1 over x minus 2. X minus 2 minus 1 over minus 1. Plus c. And I want to reiterate here. You don't really want to do all this work for this problem. I'm showing you the work so that you see how to do it. But once I got a was equal to 2 and I saw that the integral of that was going to be 2 natural log of the absolute value of x, the answer is decided for me. So I really want to stress trying to do the least amount of work possible to get the right multiple choice answer. I'm sorry, was someone saying something? I might have spoken over you.
Can you explain like how exactly you do where you found B? Because I figured everything out up until B, but I wasn't sure how to do that, like the x squared thing.
I'm doing kind of the less amount of work that I can, least amount of time. So what I'm doing, there's 2 ways you can find B in this particular example. So if you use the convenient values of x, 0 and 2 in this case, and there's still one thing left to find, you can actually plug in any other value of x you want. So one way to do this, which is not the way I did it, would be to pick anything else. I've used 0. I would usually pick 0 if I could. And if I don't have 0 to pick, I'm going to pick something like 1. I'm going to kind of pick the smallest thing I can that I haven't already used. So here's one way to do it that I didn't do it. So I could pick x equal to 1, plug in 1 for x, so I get 1 minus 5 plus 8. Equal to, plug in 1 for x, I get a, which is 2, times 1 minus 2 squared. I get b, which I'm trying to solve for, times 1 minus 2. And I get c, which was 1 times 1. And then I can solve and get, let's see, 1 minus 5 is negative 4, plus 8 is 4. Well, the 2 times negative 1 squared is 1. B times 1 times negative 1 is negative b. And 1. So 2 plus 1 is 3. 4 minus 3 is 1 equals negative b. So negative 1 equals b. That's definitely one way you could do it. It's not the way I usually do it or the way I did it here, but that is a way that works. If you've only got one thing left to find, you can just pick any other value of x that you haven't already used and solve for the unknown thing by using the fact that you found a and you found c. The way I did it was I looked at, and I'm going to erase this part here, that a equals 2 and c equals 1. What I actually did was I did what's called equating coefficients. But I tried to do it without doing a ton of work. So you can totally multiply this out and say, you've got x squared minus 5x plus 8 equals a times, if I multiply this out, it's x squared minus 4x plus 4. And I've got, if I multiply this part out, it's x squared minus 2x. So I've got b times x squared minus 2x plus cx. And if I look at just x squared, on the left, I've got 1x squared. On the right, if I distribute the a, I've got a times x squared and lower power terms, which I don't care about at this particular moment. And I've got b times x squared. And for polynomials to be equal, the coefficients of the corresponding powers of x have to be the same. So since 1x squared equals ax squared plus bx squared, I have to have that 1 equals a plus b. And then since a is 2, b has to be negative 1. So that's the equating coefficients method. But really, you should do whatever works best for you. So if it's easier for you just to plug in some random value of x, do that. If it's easier for you to equate coefficients, do that. But really, in this problem, we shouldn't have done either of these things, because once we saw that a was equal to 2, and that we were going to be, so here's what I would say about partial fractions for a multiple choice. If you're doing the partial fractions, once you get one of the things, right? So I got a equal to 2. So I was integrating 2 over x. And I know that the integral of 2 over x is 2 natural log of the absolute value of x. I'm going to go back and look at all my multiple choice answers. And I'm going to be, I feel like we're lucky here in that there was only one answer that had that, so I could stop. If, on the other hand, so let me share my screen with you guys again. Let's say we did that, but instead we got a equal to 1. So we were integrating 1 over x. Well, then natural log of the absolute value of x is what we're going to get. And that means b or d would have been a possibility. So then I would have had to do more work. I would have specifically needed to find the value of b to figure out what was over the x minus 2 to know if I was going to get this one where it was a negative 2 times natural log of the absolute value of x minus 2, or if it was this one, a negative 1. So for partial fractions with multiple choice, you can kind of narrow down which answer has to be piece by piece, so you don't have to actually do all of the work. And that's going to be kind of, I think, a big theme for FAM's test is, I mean, certainly you should go back and check your work if you have time, but I would say try to go through each problem as rapidly as possible, doing kind of, for lack of a better word, the least amount of work possible to be able to see what the multiple choice answer is. It does mean you're going to need to be extra careful to make sure your numbers are right. But that problem we just did, once we got a equal to 2, we can be convinced that, oh yeah, the only possible answer is answer C. My board sounds terrible. I'm dying. It sounds like it's not, but I feel like I need to like tighten some of these. No, these bolts were tight. This one's a little. I can stand to tighten this one. The problem is I'm missing one of the bolts over here, which actually makes it easy to do things. But yeah, that might help a little bit. All right, let's move on to problem 2. Compute the integral of x, from 0 to infinity of x e to the negative x dx. So here's something worth knowing, although I don't think this is actually the intention of this problem. This is a PDF. Is he a liar? Yes, he is. This is how, so what I want to really say is, like, I know that, right, we know that, I forgot what, I'm trying to make this too complicated, really. What I'm trying to say, just so I get this right. This is a special probability density function. I'm trying to, where did you go? I'm not sure which section this is in. 1 second, please. Oh yeah, totally. So this, we know that if you've got a e to the negative ax, that's equal to 1. Right, that's a PDF. A e to the negative ax from 0 to infinity. And we know that the mean of that is just a. So the mean is a. So look, this is how you would calculate the mean, right? Because the mean you get by doing the integral from 0 to infinity of x times your PDF. but in this case, my a is 1, right? In this example here, a is 1. And so I've got the integral from 0 to infinity of x times 1 times e to the negative 1 times x. And so what I'm trying to say in kind of a roundabout way is this integral is how you would calculate the mean of this probability density function f of x equal to 1 times e to the negative 1 times x. But we already know that the mean of this is 1. So that you say, oh, this integral is equal to 1 because it is the mean of a PDF whose mean should be 1. Now, that's probably not how I would actually, it's how I would see it. It might not be how you would see it, which is totally understandable. So again, we are trying to be fast, not to be, I don't want to say not precise. We're not trying to be super rigorous here. So normally I would say you should do the whole limit thing, right? But since we're not having to do that, here's how I would probably actually do this. I want to integrate this thing. We can use tabular, although it's only a one-step integration by parts, so you don't have to use tabular. It's only tabular. So u is going to be x, derivative is 1, derivative is 0. dv is e to the negative x. The antiderivative is e to the negative x divided by negative 1, which is the same as multiplying by negative 1. And the antiderivative of that is e to the negative x divided by another negative 1, so it's negative 1 times negative 1, which is just e to the negative x. So then I'm going to get x times negative e to the negative x minus e to the negative x. Sorry, negative. And then minus 1 times e to the negative x, because right, these just cancel out or multiply to 1. From 0 to infinity. And I'm not doing the whole limit thing because no one's checking my work to see that it's appropriate, right? If someone was going to like look at my work and grade me on preciseness, I would be writing a limit. But since it's a multiple choice, I don't think we need to do that. So here's what I would do. I would rewrite this as negative x over e to the x minus 1 over e to the x from 0 to infinity. And then you can really just plug in infinity if you want. So here, negative infinity over e to the infinity. That's going to go to 0 because the infinity on the bottom is a much bigger infinity. It's going to grow much faster than the top. So this goes to 0. Minus 1 over e to the infinity also goes to 0. Minus, then we plug in 0, and you get 0 over e to the 0, that's 0. And then you get 1 over e to the 0. So you get minus 1. So I'll repeat. I don't think you need to use limits for this improper integral if you're not having to show your work. And I will also repeat, I think he might have intended for you to see this as the mean of a PDF. So for example, if instead, so here's a question I feel like he could ask. Ooh. And I think I made a small mistake. Well, I didn't make a mistake so much as I might have said something wrong, in that the mean isn't the a value, it's the 1 over the a value. So I could see him giving you a question like this. Compute this integral. The integral from 0 to infinity of what kind of crazy thing do I want to say here? Not that crazy. I want to say, let's say I want to find the integral of 1/4 x e to the negative 1/4 x dx. Right? Right. And you could totally do this the same way we just did that previous problem. However, the fast way to do this is to be like, hey, look, 1/4 e to the negative 1/4 x is your usual probability density function on 0 to infinity. And I know the mean of this of 1 over that 1/4. But the way you calculate the mean is doing the integral of this function times x, which is exactly this. So without really having to do any work, we know that's going to equal 4 because it's the way you would calculate the mean. And we know for this particular type of thing, the mean is 4. So I would say if you see something like this, you might want to think about it. Hey, is that how you calculate the PDF or the mean of the PDF? Well, then the answer should be 1 over A. Kind of weird, but again, I think one of the things you have to think about for this test is trying to save yourself some time. Okay, let's look at problem 6. I'm just, it's not that bad. I didn't really get myself. I'm starting to pinch, but not really. So I'm going to go all the way 6 through 9, and then if you guys have other questions, feel free to jump in. Especially the Merckx folks, although again, even though this is the FAM review, I think this is just as good for the Merckx students to see. And do intend for the Merckx people to post up some questions for surface area and arclight and stuff. I just haven't written it yet, but I should be able to get that up today. So here's question 6, the integral of 3x squared natural log of x dx. So I think we should just do this by doing the integral. One way you could try to do this, which I think is not the way I would do this, is take the derivative of each of the possible multiple choice answers and see if you can get it to equal that. That is one way you could certainly get there, but I think that's too time consuming, right? Because there's 4 different possible answers and it might be the last one you try. So while you could try taking, and that's generally something that's true, you can try taking the derivative of the possible answers to see if it's which one it is, but that just might be too time consuming. So for this integration by parts, and I know it's integration by parts because I have 2 different types of things multiplied together. What am I supposed to be letting my u equal? Is it 3x squared or is it natural log of x? Yeah, right? It's always the natural log of x if you're talking integration by parts. U can be something, right? If you have something with a natural log, but it's a u substitution, then u doesn't have to equal the natural log. And then the du is going to be 1 over x dx. If u is natural log of x, what does dv have to be? What are we left with no choice? You guys are both mostly right. And in fact, here I would probably say it doesn't actually matter. Right? It's supposed to be 3x squared dx. Again, if you're not being asked to show your work, multiple choice, you probably don't need to worry about it. And then v is, of course, the antiderivative, which is x cubed. So then we throw this in here. We get uv, so x cubed natural log of x, minus the integral of vd, which is x cubed times 1 over x dx. And honestly, at this point, I'm starting to look at my possible multiple choice answers. Now, I will point out that all of the multiple choice answers have x cubed natural log of x, right? Share, dumb person. All right, so I'm looking at this problem 6 here. All of the answers have x cubed natural log of x. So we actually have to do the second part. I'm looking at the second part. We see that it should be pretty straightforward, right? There shouldn't be anything weird. So what we have to do is we have to simplify this. And that simplifies to x squared. So you got x cubed natural log of x minus the integral of x squared, which we know is x cubed over 3. So it definitely has to be answer C, x cubed natural log of x minus x cubed over 3. And that's it. The nice thing, so something kind of to take away from this particular problem is looking at this answer, right? Looking at these answers, to me says, hey, it's probably integration by parts because I'm getting this kind of format where it's something times something minus something else. And I can kind of see here, well, if this is supposed to be u times v, I know that my u should be the natural log of x, and my dv should be 3x squared, so that my v is x cubed. So looking at the multiple choice answers can kind of give you a hint as to what you should be choosing for u and v if you're not, or for u and dv if you're not quite sure, right? I'm definitely seeing natural log of x in there, so I definitely know that u should be natural log of x so that it occurs in my answer, right? I definitely wouldn't be picking dv to be natural log of x because, well, 1, it's hard to integrate, but 2, right? dv doesn't show up in the answer, v shows up in the answer. So sometimes you can use the multiple choice answers to your advantage, like in this next one. So this next one, which is the integral of x squared plus 1 times e to the x cubed plus 3x dx. I see a lot of answers. A lot of answers. Let's see. So in fact, so here's something kind of interesting. So let me share my screen again, although I imagine a lot of you have this. So looking at these answers, I see, oops, sorry, that's not what I wanted to do. Let's look back at the, where'd you go? Did it disappear? Am I dumb? I'm dumb. Sorry, one sec. Let me grab this. Okay, there we go, sorry. So looking at these potential answers, I see either answers that have the e to the x squared plus 1 exponent, or answers that have e to the x cubed plus 3x. Now, it seems like it's probably not e to the x squared plus 1 because the derivative of e to the x squared plus 1 is e to the x squared plus 1 times 2x, which is definitely not what I have, right? When you're integrating e to the something or differentiating e to the something, the exponent should never actually change. So I know it's definitely not this first answer. It's probably one of these other answers. So I'm just gonna look at B because each of these other answers just differ by a constant. So if I take the derivative of B and don't get what I want, I know how to fix it. So I'm actually not gonna do the integral here. I'm gonna say, I think the answer is B, which is actually wrong, but I'm just gonna pretend like I think the answer is B. So I think my answer is e to the x cubed plus 3x. I'm going to leave off the plus c because I don't really care. And I know that the derivative of this, well, I'm actually going to find the derivative of this. So the derivative of e to the x cubed plus 3x is, well, the derivative of e to the stuff is e to the stuff times the derivative of that stuff, which is 3x squared plus 3. Okay, so let me ask you guys. Is the derivative of this equal to my integral? Or equal to the integrand, I should say. Yay or nay? Oh, sorry, you guys might not be able to see it. Sorry, I forgot to stop sharing. No, it's definitely not, right? So what would I need to do to this so that the derivative of this was equal to this?
Factor out a 3.
Sure. So you're definitely right. But what I want to say, so let me ask you guys this question. Do I need to divide this by 3 or multiply this by 3 so that this answer ends up actually being this? Exactly. I need to divide by 3. So my actual thing that I wanted should be the derivative of 1/3 e to the x cubed plus 2x, because then this 1/3 here will cancel out the 3's there, and I'll have an x squared plus 1. So that tells me that my answer for this part has got to be part D, because D is the one where it's e to the x cubed plus 3x divided by 3. Now, we certainly could have done this by actually doing the u sub, but I don't think you have to here. I think it's faster to just take the derivative of the thing I think might be the answer, and then if it's not, fix it by just dividing or multiplying as needed. I can do this one the long way if you guys want me to, but I think, again, I think the real essence of your final is to try to be as efficient as possible. Okay, problem 8 looks real super not fun. But probably has something like this. So problem 8. A company expects its income during the next 5 years to be given by C of t equal to 100,000 t for t between 0 and 5. So I'm going to write that down. Now, and I don't remember if you said, is your test open note or closed note?
It's closed note, but we get a formula sheet, so we get the formula for how to do this problem.
Oh, thank God, because I never remember the formula. So assuming an annual inflation rate of 4%, so 0.04, can the company claim the present value of this income is at least $1 million? Okay, so let's go ahead and look at the formula for present value. So the formula for present value is just given, right? The potentially useful formulas. It's the integral from 0 to t. This is just what's on the formula sheet. 0 to t1 of c of t e to the negative rt. dt. That's the present value. So in this, sorry, we've got t between 0 and 5. So in this particular problem, the present value is going to be given by the integral from 0 to 5 of c of t, which is 100,000 t, e to the negative 0.04 t dt. What kind of calculators are you guys allowed to use? Because I could see just throwing this in a calculator and doing it that way.
We're not allowed to use calculators.
Okay, nice. All right, so this isn't too awful. It is, again, integration by parts. And so the answer is just yes or no, guys. So clearly, right, he's giving you some numerical facts that 1 divided by 0.04 squared is 625, and that e to the negative 0.02, okay, sure, is sometimes some gross stuff. Clearly, the point here is that he wants you to actually do the integration. So here's what I would do. I would factor out the 100,000. Yeah. So I'd rewrite this as 100,000 integral from 0 to 5 of t e to the negative 0.04 t. Oh, okay. I see where he's getting 0.2. So again, right, looking at the useful information he's giving me, I'm seeing an e to the negative point. I think he made a mistake there. I'm gonna see if I think that's a mistake, which is fine. We can fix it. Except it's not fine if he makes that mistake on an actual test. So here's what I'm seeing, right? I'm seeing that I'm going to integrate this and eventually plug in 5, and 5 times 0.04 is 0.2, not 0.02 like it says on the test. So we'll fix that in a second here. So I would do this using tabular because I think that's easy. So my u is t, and then the derivative is 1 and then 0. My dv is e to the negative 0.04 t. The antiderivative is e to the negative 0.04 t divided by negative 0.04. And the antiderivative of that is e to the negative 0.04 t divided by another negative 0.04, so 0.04 squared. And I didn't keep the sign because a negative times a negative is a positive. So here's what we're going to get. We're going to get 100,000 times, so let's see, I'm going to have t times e to the negative 0.04 t over negative 0.04. That's gross. Minus 1 times e to the negative 0.04 t over 0.04 squared. So just e to the negative 0.04 t over 0.04 squared from 0 to 5. So let's look at what happens here. Sorry, I'm kind of out of room. I'm gonna go up to the top. Go up top. Yeah. So I've got 100,000 times, when I plug in 5, you get 5 times e to the negative 0.04 times 5, which is e to the negative 0.2 over negative 0.04. And then plugging in 5 here, I get, gosh, this is going to be dumb, minus e to the negative 0.2 over 0.04 squared. And then minus, plugging in 0, plugging 0, I get a 0 here. Plugging in 0 here, I get a minus e to the 0, which is 1. So you get a 0 minus 1 over 0.04 squared. And then we have to try and use what's, so, oh, you're not allowed to use a calculator, which is also dumb. So looking at what he's given us, okay, so he's kind of given us this piece here. We need to factor out the e to the negative 0.2. So doing this, I get 100,000 times, I factor out e to the negative 0.2 from this part here. I'm left with a 5 over negative 0.04 minus a 1 over 0.04 squared. So I need to factor out a minus sign as well, because right, so let me share my screen with you guys just for those of you who don't have it. The useful information here is that e times, so e to the negative 0.02, which again should be 0.2, times 5 over 0.04 plus 1 over 0.044, which is exactly what we have, except I have negative signs, is about 614. So what we have here is that I have 100,000. I'm sorry, I forgot the other piece. God, this is a dumb problem. It's just unnecessarily unwieldy. Minus and minus is plus this number, and that number he does actually tell you is exactly 625. Okay, so here's what I got. Here's what I think I've got. I've got this, and again, this part here, I'm just negative of what it should be, so that should be approximately negative 614 according to what he's got, plus 625. And so we end up getting negative 614 plus 625 is 11, so we get approximately 100,000 times 11, which is bigger than a million. So the answer should be yes. Let me look at the solutions real quick just to see if he addressed the fact that he made a little error there. No, he just said, oh no, he does look down here. Yeah, he does not address it, but he does. Yeah, okay. So if one of you might point out to him, if you have the desire to, that there is an error on that problem, just so that kind of error doesn't happen on the actual final exam, because I would find that confusing as a student if I was seeing e to the negative 0.02, but I knew I was supposed to get e to the negative 0.2. So just something you might want to bring up with him if I would encourage one of you to bring it up with him, because I would like to not have you guys have to deal with mistakes on your actual final, because it can make it harder to figure out what's going on. Okay, let's look at problem 9, which is the last problem on his practice exam. Find the equation of the tangent line of y equal to this growth. Oh yeah, I was looking at this one the other day. I was like, what? And then I was like, oh, I know what you guys are supposed to do. So this problem is dumb, but not really. I'm supposed to find the equation of the line tangent to y equal to x squared minus 3, quantity to the 5th, times the square root of x cubed minus 4, all over x. So we want the equation of the tangent line at the point 2, 1. 2, 1? Yeah, 2, 1. 1, 2. Sure, okay. And so the idea here is that we have to find the slope of the tangent line, right? Because once we know the slope, let's call that m, the equation is just going to be y minus 1 equals m times x minus 2. So how do we find the slope? Well, we find the slope by taking the derivative. The issue here is that the derivative is really ugly, right? It's a really gross quotient rule thing, and you could totally do it that way, but it would be time consuming. And again, for this test, I think you really have to be judicious with your use of time. When you see y equal to something gross like this, specifically a gross quotient with lots of different factors. Sorry, my pants are like weirdly sitting. The idea that he is trying to get you to use is to use the logarithmic differentiation. Even though it's not x to a power with an x in it, you can still use logarithmic differentiation if you ever have something that's complicated with when you have lots of multiplying or dividing. So we can take the natural log of both sides. I'm going to write this as x cubed minus 4 to the 1/2 all over x. And then the idea is that before you take the derivative of both sides, you have to break up the right-hand side using the rules of logarithms. So I can rewrite the right-hand side as the natural log of x squared minus 3 to the 5th plus the natural log of x cubed minus 4 to the 1/2 minus the natural log of x. Any factors in the top end up with a positive natural log of that factor. Any factors in the bottom end up with a negative natural log of that factor. Are there questions about this step in particular? Okay. So then you could take the derivative of both sides here, but I think it is definitely worth your time to bring down the powers. It makes things simpler. So I'm going to write natural log of y equals 5 times the natural log of x squared minus 3 plus 1/2 times the natural log of x cubed minus 4 minus the natural log of x. We cannot bring down this power or this power. It has to be the power on the entire thing like this. So now we differentiate. The derivative of the natural log of y, if we're differentiating with respect to x, is 1 over y times y prime. The derivative of the right-hand side is 5 times the derivative of the natural log of some stuff is 1 over this stuff times the derivative of the stuff. Which is not 3, that's crazy. It's 2x. And then over here I get 1/2. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, which is 3x squared. And then finally, minus the derivative of the natural log of x is 1 over x. And at this point, you could rewrite, right? So often when we find the derivative this way, we then multiply both sides by y, and then plug in that y is equal to this gross thing here. We don't have to do that here, because we're not trying to find the derivative in general. We're trying to find the slope of the tangent line at this one point. So at this stage here, I would plug in x equal to 2 and y equal to 1. I'm going to erase this. I have some room because I don't want to leave this side of the board. So look at what I get. If I plug in y equal to 1, I get 1 over 1. Get 1 over 1 times y prime. So I don't even have to think about multiplying this over because it's just 1. On the right-hand side, I'm going to plug in 2 for every instance of x. So I'm going to get 5 times 1 over 4 minus 3 is just 1 over 1 times 2 times 2. So 2 times 2 is 4. And here I get 1/2 times, plugging in 2 for x, I get 2 to the third is 8 minus 4 is 4. So I get 1 over 4 times 3 times 2 squared. And then plugging in 2 for x, I get 1/2. And that's definitely what he wants you to do. So I'm going to get y prime equal to 5 times 2 times 2 is 20. Plus, let's see, 4 and 4 cancel, and I get 1/2 times 3, which is 3/2, minus 1/2. So I get y prime equal to 20 plus 3/2 minus 1/2 is 1, so I get 21. And then that is my slope of my tangent line, and that's what's going to go right there. So my answer would be y. In fact, so instead of trying to do too much work, let's look at the possible solutions. So looking at the solutions, I see only one. Oh, sorry, let me show you guys solutions. Sorry, I'm looking without you guys looking. So looking at the solutions here, I see only one answer that could possibly fit with what I've got, right? I've got this answer C again is the only one that has a slope of positive 21. So that's gotta be my answer. And it is, right? Because that's essentially what I've got. Y minus 1 equals 21 times x minus 2. He just brought the 1 over to the other side. So again, if you can see the possible answers, you should definitely use that to your advantage, right? If you see that they all have different slopes, you really only have to find the slope, and you don't have to even worry about thinking about what the equation of the line is. So you'll be like, oh, I know the slope is 21. I know the answer is the one where the slope is 21. So although multiple choice tests in math generally are kind of not the best, there are some things to your advantage when it comes to a multiple choice test. Specifically, you can kind of narrow down answers if you see what the possible answers are. You can definitely use that to your advantage. Whether it's taking a derivative to compute an integral instead of actually computing the integral, or doing what we just did where we said, oh, I know the slope's got to be one of these numbers, so I'm just going to find the slope. I will say for problem 9, you really don't want to do that one the long way. taking I erased the original function. Taking the derivative of the original function without using logarithmic differentiation is definitely not impossible, but it is messy, and it's really easy to make a mistake doing it that way. So if you see something like that, that is definitely what he wants you to do, and probably going to be the easiest way to do it. I don't think. There are other. No, that's the only way you should do it. Don't be dumb. I was trying to think of something else. To be too clever. You don't want to try and be clever. You want to try and be straightforward on your exam. Okay, so that is. I mean, we could go do the first couple questions of the FAM test or practice exam if you guys want, or if there are other questions you guys have, I'm happy to address any other questions. Actually, I would like to look at problem 3 for just a sec, if nobody minds. So I'm gonna share my screen with you. I know we never talked about, at least I never talked about with you guys, the uniform probability distribution function, which problem 3 definitely is an example of. So problem 3 says find the mean and median of the probability density function f of x equal to 1/18 on the interval from 0 to 18. For a probability density function that is uniform like this, where it's just equal to a constant, it's kind of like the best case scenario. And I'm still sharing my screen, so stop doing that for 1 second. So in that case, right, stop sharing. Right. Oh, when do you time this? Okay, that is so, Sophia. That is an excellent question. That's not a short answer. Let me finish. So let me finish problem 3, and then I'll try to address your question. So for problem 3 here, if you've got f of x equal to 1/18 on the interval from 0 to 18. But you've really just got this kind of deal. Here's 18, and here's my f of x equal to 1/18. So the area under the curve is just 1, right? It's a rectangle that's 18 long and 1/18 high. And so the median is definitely just the halfway point, because it's uniform on both sides. Halfway is going to give you half the area on the left, half the area on the right. So the median here is whatever the halfway point is between your endpoints. So the median is just the average of your endpoints and the mean is the same, or the expected value or the mean is also going to be, for a uniform distribution like this, it is also going to be the average. So for a uniform distribution, the mean and the median are just the same. For a PDF, are the mean and median the same? Oh, no. So it is definitely not true that the mean and the median are always the same. It is true if you have a symmetric distribution. So if you have something like this, or the example that I did a couple classes ago, where it was like f of x was something like, I think it was 3/256 times, I think it was x minus 2 times 10 minus x. 10, yeah, that seems right. So it was a downward opening parabola, and it had intercepts at 2 and 10, 4, 6, 8, 10. And parabolas have this quality of being symmetric about their axis of symmetry. So here, the axis is definitely at x equal to 6. And not only does it cut the area in half the area is on the left, half the area is on the right, it's also cutting it in a balanced, symmetric way. So if that's the case, you can definitely say, oh, well, the mean and the median are the same. On the other hand, if you have something more like an exponential distribution that does something maybe like this, it's definitely not symmetric. And so even though the mean is like something like this, right, it's definitely not a place where it's necessarily, the median might be something like that, right? That's where there's half the area on the left, half the area on the right. That's not necessarily where the areas would balance out. But I do literally mean balancing like on a teeter-totter. So hopefully that kind of answers your question, Nicole. So it's not so much that it's coincidence, it's that symmetric shapes like this always have a mean and median equal to each other. And asymmetric shapes, I don't think ever can. Okay, so Sophia, you asked a very good question. When do I know what to use tabular versus U sub versus partial fractions versus integration by parts? All right. So I will say tabular is just integration by parts. It's just a very kind of special kind of integration by parts that only applies to 3 different types of integrals. So integration by parts. So so I usually look for a U sub first. So I look for U sub, and I know I want to do a U sub when the derivative of one part is another. So the derivative of U, of our choice for U, is also present. An example of this would be like the integral of x squared times e to the x cubed. Or the integral of x to the 4th times cosine of x to the 5th. Or the integral of, sine of the natural log of x over x. In each of these cases, there is a choice for u whose derivative is also in there. In this one, I would choose u equal to x cubed because the derivative of x cubed is 3x squared. And I essentially have 3x squared. I mean, it's just x squared. I don't care about the constant multiple. We can always adjust for that. For this one, same idea. I would choose u equal to x to the 5th because the derivative of x to the 5th is 5x to the 4th, and I essentially have a 5x to the 4th. I don't care about the 5. Here, the choice for u would be natural log of x because the derivative of natural log of x is 1 over x, and I have a 1 over x. So the choice for u is always something we hope whose derivative is also in there. The other way we think about choosing u is it should be something that's stuck inside a function. This natural log of x is stuck inside the sine function. This x cubed is stuck in the exponent of e to the whatever. This x to the 5th is stuck inside the cosine function. So that's how I pick a u sub. For integration by parts, it's more that you have a mixture of types of functions multiplied together. But it should be multiplied. I guess division is also sometimes okay. So some examples of this would be the integral of x to the 4th times natural log of x dx, or the integral of x times sine of x dx, or the integral of I'm going to say e to the x times cosine of x, even though I would hope that you wouldn't get that one. So each of these are examples of integration by parts. Here, so for this first one, you would let u equal natural log of x, dv would be x to the 4th, and the rest. Here, u would be x, and dv would be sine of x. And here, this one's terrible. This is the one where you have to do it twice, then you get back what you started with. So you can do it either way. Here, you'd let u equal cosine of x, and dv would be e to the x. But then you have to do it again. This one kind of sucks. So integration by parts is just things multiplied together where you let u equal one part, dv another. And then specifically tabular is still integration by parts, but it's specifically 3 different kinds of integration by parts. It's x to a power times either sine or cosine or e to the x. So it's the integral of x to a power times cosine of x, or x to a power times e to the x, or it can actually be e to the 2x or e to the something times x, or x to a power times sine of something times x. These are the 3 situations where you can use tabular, and only those 3. You can't do it for any other combination of functions. Just x to a power times sine or cosine or e to the whatever. And then finally, partial fractions kind of looks like none of those. Oh, that's not entirely true. Let me show you 2 different problems. One's partial fractions and one is not. So let's look at this. Let's look at the integral of 2x over x squared plus 4 minus 4 versus the integral of 2x plus 1 over x squared minus 4. One of these problems is a partial fractions problem, and one of them is not. Well, I shouldn't say not. They both could be partial fraction problems, but partial fractions is often what I refer to as a method of last resort or later resort, in that you want to kind of do other stuff first, because partial fractions kind of sucks. So if I can, I'm going to do something else first. And for this one here, although I could do partial fractions, because the degree on top is less, the degree on the bottom is bigger. I should say the degree on the bottom is bigger, yeah, strictly bigger. If the degree on top is bigger or equal, then you can't before you do polynomial division. But here, since the degree on top is actually less, right, it's 1 degree on top and the second degree on the bottom, I should say a first degree on top, not a 1 degree. Okay, so since the degree on top is less and the denominator factors, it has to factor. If you can't factor the denominator, you can't use partial fractions. Since the degree on top is less than the degree on the bottom is bigger and it factors, you could use partial fractions, but before I even think about that, I should ask myself, can I do something easier, like a U substitution? And here I definitely could do a U sub with U equal to x squared minus 4 and du equal to 2x dx. I feel like I did this one too easy. I should have just made it x instead of 2x, but that's the idea, right? This one would definitely be a U sub. And you would end up getting, right, this would be the integral of just du over u, which would be the natural log of the absolute value of u plus c, which would be the natural log of the absolute value of x squared minus 4 plus c. On the other hand, this other one you cannot, because if you let u equal the denominator, the derivative of the denominator is not exactly the top or a multiple of the top. So this one we would have to do partial fractions. You have to factor the denominator, x minus 2 times x plus 2, and set this equal to a over x minus 2 plus b over x plus 2. So if you're thinking partial fractions, you should at least do a cursory check to see, could I actually just do an easy u sub where u is the denominator and du is the top or something times the top? Often, no, I wouldn't say often. If someone's trying to be kind of sneaky, they can give you a problem like that. Again, if you wanted to, you could totally do partial fractions for this one. It's just more work, I think. So hopefully I think that's a good answer to your question, Sophia. I can finish this problem off if you guys want, right? So let's multiply both sides of the denominator. 2x plus 1 equals a times x plus 2 plus b times x minus 2. I pick x equal to 2. And get 4 plus 1 is 5 equal to a times 4. So a is 5/4. I pick x equal to -2. I get -4 plus 1 is -3 equal to b times -4. So b is going to be 3/4. And so then this integral is going to become the integral of 5/4 over x minus 2. Plus 3/4 over x plus 2, which is just going to be 5/4 natural log of x minus 2 plus 3/4 natural log of the absolute value of x plus 2 plus c. Yeah, so good question. And I mean, it definitely can be challenging to kind of tell which method of integration to use. But I would say keep those guidelines in mind, and that should be somewhat helpful. Other questions you guys have? Something else. And so FAM final is Friday, right? Sorry, I lost you guys. So FAM final is Friday. So I'll try and post up my finals and pre-finals availability sometime today or tomorrow. I'm thinking, so usually Thursday afternoon, I have office hours from 1:30 to 2:30. I will definitely have those. I might even extend them a bit if people have questions, because you guys have your test on Friday. And it's, what time is your guys' test on Friday? For fan people.
So because we use Examity, like we have from like, I think like 7 a.m. until like 12 p.m. or 12 a.m. But he extended the like day. Well, it hasn't been shown on Examity yet, but he like extended it, so I can do it from Friday till Wednesday, or the last day of school.
Oh, okay. All right. So I'll definitely be available Thursday afternoon for you guys. Mercs people also welcome to come ask questions on Thursday afternoon. Then what I'm guessing is a lot of you are going to be having to take it Friday morning. Not that you couldn't take it later. So I'll be available Thursday afternoon. I will also have other availability throughout the week. But that might be, well, not that you couldn't come ask questions. It'll be more for other students, including Mercs, because Mercs' test is on the 10th, which is a week from tomorrow, so Wednesday. All right. Yes, I will, let me write myself a note so I actually do the things I say I'm going to do. Final exam dates. My availability. I will be available Thursday afternoon, especially for the fan people, because you guys all have a test that you may need to take on Friday or on a later date. There's something else I want to mention there. Thursday in class, we can certainly do more review. If you have specific questions you want to ask, don't hesitate to come with them. I know we focused more on the fan people today. So Thursday, we can certainly give more attention to the Mercs folks. If you guys have questions, we can also still give attention to the fan folks because you guys have your test on Friday. I think that's all I've got to say. Here's the attendance again. Please do go fill it out. Also, please fill out the end of quarter evaluation. If you guys have questions, don't hesitate to start a discussion or shoot me an email or whatever. But I think, oh, no. Yeah, and I will, sorry, I got my brain just, I will definitely also try to post some arc length and surface area. And I feel like there was one other thing I specifically, maybe some shell method questions to you for the Mercs people specifically, because I imagine some of that stuff will show up on your final because. So I'll try and get that posted up sometime today so that you guys have that additional resource. And yeah, I'll see you all on Thursday. Best of luck studying for your finals.
Thank you.
You're very, very welcome. Good to see you guys.